All right, we're going to continue our exploration of Hess's law, but we're going to use it in a slightly different way. But before we do that, I think it's really important we discuss about why Hess's law works. Hess's law works because change in enthalpy and enthalpy are state functions, meaning that if I have a group of compounds, and they have a enthalpy of HR, and I have a group of products that they change into, and they have an enthalpy of HP. Because their enthalpy depends only on their current state and not how they got there, that difference between the reactants and the products is going to be the same whether we had intermediates with this energy and then dropping down to that energy, or if I had intermediates with this energy that then had to go up to get to that energy. The height difference, or the enthalpy difference between the reactants and the products, is the same regardless of whatever path we take to get between the two, because that enthalpy of the products and the enthalpy of the reactants is a state function. And that's the reason all chapter long we've been stressing what a state function is. You're probably wondering why in the world we dropped that definition on you so early in the chapter. It's because it's what explains and what justifies Hess's law. Because the enthalpy of the reactants is constant and the enthalpy of the products is constant, the difference in enthalpy between the two is going to be constant regardless of the path taken to get from point A to point B. And that's why Hess's law works in a nutshell. Speaking of nutshells, I don't think there's a bigger one in the DC universe than Clock King. Talk about a mort of the month. Why don't you write down Clock King? Write down Clock King, although he has appeared in Season 1 of Arrow. Clock King. We need to define a new term, and that's standard heat of formation. Standard heat of formation is represented by our delta sign, our enthalpy H, not for standard state, and that F should really be over there. Hi, baby F. All right, and a subscript F. The standard enthalpy of formation is the enthalpy change for the formation of 1 mole of a substance in its standard state from its constituent elements in their standard states. Couple really important parts to this definition. First, what do we mean when we say a substance is in its standard state? Its standard state The standard heat of formation is the enthalpy change for the formation of 1 mole of a substance in its standard state. Standard state is how a substance exists naturally at 1 atm and 25 degrees Celsius. For example, what do you think the standard state of water is? Standard state of water would be liquid, right? Because that's how it wants to exist at room temperature. How about oxygen? What do you think the standard state of oxygen is? Take a deep breath. Oxygen exists as a diatomic molecule and as a gas. So the standard state of oxygen would be a diatomic gas. Some other standard states that you need to be familiar with here. All right, some other standard states you're responsible for knowing are the ones that you learned last semester. You learned things in their standard state, you just didn't realize it. For example, no! I can't believe I forgot the halogens are diatomic. Last semester you learned that the standard state of nitrogen, oxygen, hydrogen, fluorine, and chlorine were all diatomic gases. You also know that your noble gases are all gases. You know that most metals are solids, right? You know their standard state. One that you may be surprised by is sulfur. Sulfur is a solid in its standard state, but it exists as a rhombic compound. It exists as a molecule of 6 oxygen atoms to form a solid powder. So that's what we mean when we say standard state, how it exists at room temperature. For example, the standard state of water. Well, we already did the standard state of water, so let's continue on here. Bye-bye. All right. So those are the standard states of some elements. If we look at this definition again, the standard state of formation, the enthalpy change for the formation of 1 mole of a substance in its standard state from its constituent elements in their standard states. So, if I am talking about the enthalpy of formation of methane, I'm talking about the reaction needed to form 1 mole of methane from the elements that make it up. What elements make up methane? Carbon and hydrogen. So I have to make it up from carbon and hydrogen. I can't make it up from other compounds. In a standard heat of formation reaction, no reactant compounds. Only elements as reactants. Not only that, but these elements, carbon and hydrogen, have to be in their standard state. So hydrogen has to be a diatomic gas. So it has to be diatomic and a gas. And carbon not only has to be a solid, but it has to be graphite. If you look on a chart, you'll see that you'll see several forms of solid carbon. Has to be solid carbon. Graphite. All right, let's take a look at some examples here. Write the equation associated with the standard enthalpy of formation of water. All right, think of our definition. First, we can only form 1 mole of product. So we know we're going to form water. What's water's standard state? Liquid. So we want to form 1 mole of liquid water. We have to form it from its elements. So we have to form it from hydrogen gas and what's oxygen's standard state? It's a diatomic gas as well. Now, we have to balance our equation. Remember, when we balance our equation, we can only have 1 mole of our product. So we can't change the number over here to balance. We can only change the numbers over here to balance. Because of this, you will use fractions in balancing. In thermochemical equations, you'll often see fractions in balancing. And this is an example of one where we'll have to do that. When we look at our balancing, we have 2 hydrogens here, 2 hydrogens here. So our hydrogen situation's okay. But for oxygen, we only have 1 over here. Because we have to keep our number of moles of water at 1, we can't multiply our water molecules. Instead, we have to bring down the number of oxygen atoms over here. So we're going to put a 1/2 out in front to balance it. So 1/2 times 2 is 1. So now we have the same number of oxygen atoms. And that would be the equation associated with the standard enthalpy of formation of water. Which of the following chemical reactions corresponds to the heat of formation of liquid ethanol? All right, so if we're wanting a heat of formation of liquid ethanol, the first thing I always check on these, well, let me also stress, you'll get a lot of these questions on in exams. Even if you don't get one on one of my exams, the ACS loves these questions. I don't think I've seen an ACS standardized exam that hasn't asked one of these questions. So let's take a look here. We want the heat of formation of liquid ethanol. So the first thing I'm going to do is I'm going to eliminate any equation that doesn't have 1 mole of ethanol as a product. All right, this first equation A has lots and lots of products, so I know that's out. Same for equation 2. Well, it looks like equation C, D, and E are all still in the running because they all have just 1 mole of ethanol. All right. The second part of that definition is that we have to make the ethanol from its constituent elements. What elements make up ethanol as we look at it? We look at it, we see carbon, we see hydrogen, and we see oxygen. So we should only see elements on the other side, on the reactant side of our equation. Let's see. This equation only has elements. Good. This equation only has elements. Good. This equation only has elements. So far, so good. So the next thing we have to check is, are the elements in their standard states? Remember, the standard state of carbon is graphite or a solid. Hydrogen is a diatomic gas in its standard state. So is oxygen. So we need to check, is carbon solid graphite? Winner, winner, chicken dinner. Next, is hydrogen a diatomic gas? Oh, look at that. Hydrogen's a liquid there. Bye-bye. Hydrogen's not in its standard state there. Let's look at our second equation. Hydrogen's a gas there, and it's diatomic, so we're good. Our last equation, hydrogen's a gas, but it's not diatomic. So, bye-bye. That leads us with one equation. Let's go ahead through with our checklist. Is our hydrogen in a diatomic gas? Yes. Does it balance? 2 carbon, 1, 2. 6 hydrogens, 3, 5, 6. Good. 1 oxygen, 1 oxygen. Winner, winner, chicken dinner. Speaking of chickens, I'm not sure there's a bigger chicken in all of comic books than the Acrobat. Write down the Acrobat. The Green Arrow villain, the Acrobat from 1961. The Acrobat. Hopefully you finished writing down Acrobat and are ready to move on. One of the reasons we care about the standard enthalpies of formations is you can find tables and tables and tables of the enthalpies of formation. And what we're going to discover and show you in a second is that if you know the standard enthalpy of formations of the substances in an equation, you can use them to solve for the enthalpy change for the equation. Matter of fact, let me spoil the punchline for you right here. The change in enthalpy for a reaction is equal to the sum of the enthalpy of formations of the reactants, of the products minus the sum of the enthalpy of formations of the reactants. Using this formula, which is basically based on Hess's law, a restatement of Hess's law, we can calculate the change in enthalpy of any reaction as long as we know the enthalpy of formations of its products and of its reactants. And therefore, there are tables and tables of enthalpies of formation. Let me ask you one of my favorite questions. One of my favorite test questions: what is the change in enthalpy of formation of oxygen gas? The question becomes to you is, do you see oxygen on the chart anywhere? No, you don't. Does oxygen gas have to form at 25 degrees Celsius and 1 atm of pressure? No. That's how oxygen exists naturally at that temperature. Additionally, oxygen is an element, so you can't form it from something else. So the enthalpy of formation for oxygen gas is 0. What's more, the enthalpy of formation is equal to 0 for all elements in their standard states. The enthalpy of formation is 0 for all elements in their standard states. It's not true for compounds, right? Water is a liquid naturally at room temperature, but it still has an enthalpy of formation. Why? Because it's not an element. It has to form from elements, right? It has to break bonds of hydrogen and oxygens and reform them. So compounds will never have an enthalpy of formation of 0, but elements in their standard states have an enthalpy of formation of 0. I knew I was getting ahead of myself, but the whole reason we've been looking at these standard enthalpies of formations is that the standard enthalpy of formation for a reaction is equal to the sum of the enthalpy of formation of the products minus the sum of enthalpy of formations for the reactants. And this is what I get for using publisher overheads. They forgot the summation signs. Let's take a look at an example. Using the standard heats of formation, calculate the standard enthalpy of reaction for the photosynthesis of glucose from oxygen and carbon dioxide and liquid water. The first thing I like to do is when I know I'm going to be using those standard heats of formation, I like to go to a table and look them up. And then I focus on the math once I've looked them up. Alright, so I go to that table, and remember, if you go back 2 or 3 slides in that packet that you've undoubtedly printed out to take notes on, you'll see table 8.2 with those standard enthalpies of formation. We look up carbon dioxide gas, and we see it has a standard enthalpy of formation of a negative 3. Hey, that's a pretty neat 3 for me. 73.5 kilojoules per mole. Then we look up the standard enthalpy of formation of water. And when we do that, we have to make sure we have water in the right phase. We have liquid water, so that's going to be a negative 285.8 kilojoules per mole. Then we look up glucose, and it's going to be huge, a negative 1,273.3 kilojoules per mole. And then we come to oxygen. Oxygen, remember, is an element in its standard state, meaning at 25 degrees Celsius and 1 atm of pressure, oxygen exists as a diatomic gas. And since it's an element, it's not formed from anything else, therefore its enthalpy of formation is 0, because that's how it exists naturally under those conditions. So now I've gone to a table and I've looked up the enthalpy of formation of everything. Next, my formula that I'm going to use, of course, is the standard enthalpy change for the reaction is going to be equal to the sum of the standard enthalpy of formation of the products minus the sum of the standard enthalpy of formation of the reactants So now it just becomes a matter of plug and chug and accounting. Most people, when they work these problems, have trouble with the accounting aspect, keeping track of all those numbers, keeping track of those negative signs. So if we look at our formula here where they've broke it down symbolically, we have our products, and our first product is our glucose. So the enthalpy of formation of our glucose, we looked that up. We have 1 mole of glucose. Then we have to account for our oxygen. We have 6 oxygens. They have 0 kilojoules each. Well, gee whiz, 0 times 6, and of course that's just going to go to 0 there. Minus the enthalpy of our reactants. We've got 6 carbon dioxide, so 6 moles of carbon dioxide, each with an enthalpy of formation of a negative 393.5 kilojoules. Plus 6 moles of water, and our water has an enthalpy of formation of a negative 285.8, and we have 6 moles of them. Alright, so I'm going to simplify my terms one at a time here. Grab my calculator, and I take 6 times 393.5 negative, so I've got a negative 2,361 kilojoules, plus, and then I have 6 times 285.8 negative, so I've got a negative 1,714.8. That's a 0.0 if we're keeping track there. All right. I'm just getting sloppy. I'm dropping things. I've got a little bit of a cold, in case you can't tell from my voice here. No, you always sound like the pimply-faced team on The Simpsons, so we really couldn't tell from your voice. So I'm minusing a negative. Calculator syndrome here, just a second. Got a negative 4.0758 kilojoules, and a negative times a negative is a positive. And that's going to give me a delta H of a positive 280 to 0.5 kilojoules for my standard change in enthalpy. I've had a couple questions about units on these questions before, and here's what's happening. All your enthalpies of formations, all these, well, first of all, that's our big answer right there, right? All of our enthalpies of formation have units of kilojoules per mole. And when we multiply by this 6 here, we're technically multiplying per mole. So that changes our units when we're doing our calculations to just kilojoules. However, this standard enthalpy of formation is really written in relationship to that equation there and how it appears. So that changes our units by convention, because it's in relationship to a chemical equation, as our standard units. That having been said, you'll often see people get sloppy and not put the kilojoules per mole, or you'll often say, okay, people know it's kilojoules per mole and we're just going to write units of kilojoules there. But very technically, the end of result of our calculations has units of kilojoules, but we write it like that because we're writing it in relationship to a balanced chemical equation. And that's it. Chemistry's easy, life is hard. Before we do anything here, why don't you write down Merlin? One of Green Arrow's enemies has the name Merlin, M-E-R-L-Y-N. Matter of fact, that's the one who John Behrman plays on the show. M-E-R-L-Y-N, Merlin. Now that you've written that down, let's take a look at this example. Here, we're wanting to solve for the change in enthalpy for the reaction of natural gas with oxygen to produce carbon dioxide and water. Once again, we're going to use our standard enthalpy of formations to help us accomplish this task. So we have to go to a standard table and look them up. This time, your standard table doesn't actually give you methane. You have to go to your book for that. But if you looked up your standard enthalpy of formation for methane from your textbook, you discover it to be 74.8 kilojoules per mole. Oxygen's an element in its standard state, so it has an enthalpy of formation of 0. Then we have carbon dioxide, and carbon dioxide has a standard enthalpy of formation of a negative 393.5, and yes, you'll probably have that memorized by the end of the semester from doing all the homework. And then you've got water, and liquid form water has an enthalpy of formation of a negative 285.8 kilojoules per mole. Where did all these values come from? They did not come out of thin air. They came from a table, right? We went to a table and looked them up. All right, so now we need to plug and chug. Our formula, as always, is the enthalpy of change of enthalpy formation for a reaction is equal to the sum of the enthalpy of formations of the products minus the sum of enthalpies of formation of the reactants. If we break it down like your book does symbolically, it's going to be the enthalpy of formation of carbon dioxide plus the enthalpy of formation of the water minus the enthalpy of formation of the natural gas. So we start with our products. We've got carbon dioxide, and we have 1 mole of carbon dioxide, and its enthalpy of formation is negative 393.5. In addition to carbon dioxide being formed, we form 2 moles of water. So we have to include that number of moles in our calculations, right? So we're going to multiply 2 times the enthalpy of formation of water. Minus the enthalpy of formation, the sum of the enthalpy of formation of the reactants. Well, of our 2 reactants, oxygen has an enthalpy of formation of 0, so that leaves us with 1 mole of methane to deal with. All right. Put that into your calculator and you plug and chug. That equals a negative 965.1 kilojoules per mole plus 74.8 kilojoules per mole and that gives me a negative 890.3 kilojoules per mole. Chemistry's easy, life is hard. One more example here. Heats of formation for each of the components involved in the dissolution of sodium chloride are listed below. What is the heat of dissolution of sodium chloride? First of all, just to make it painfully obvious here, what they're asking for is the change in enthalpy for the process shown. With that in mind, why don't you pause me for a second, try it on your own, and then watch and see if I got the right answer. Did you pause me? You didn't pause me. You just kept on listening. You know that this lecture has to be ending soon, so you just thought, I'm tired, I've been listening to this guy drone on for over an hour now. Hopefully he'll shut up and solve the problem. No, pause me and try it on your own. You still didn't do it. You're still listening. Okay. Don't say I didn't beg you. Alright, so let's work this through real quickly. We've got the standard enthalpy change for the reaction is going to be the sum of the enthalpies of formation of the product Alright, now it's a matter of plug and chug. Our products are sodium, and we only have 1 of our sodiums. And our chlorine. Our chloride, sorry, forgive me there. Minus our reactants, and our reactant, we only have 1, our sodium chloride. And a negative times a negative is a positive there. So I plug everything into my calculator. and I come up with 4 kilojoules per mole. So a very small enthalpy change, slightly endothermic, which is typical for dissolving an ionic compound. Before we end this lecture, though, please write down onomatopoeia, the green arrow villain created by Kevin Smith. Onomatopoeia, O-N-O-M-A-T-O-P-O-E-I-A. Onomatopoeia. O-N-O-M-A-T-O-P-O-E-I-A. Onomatopoeia, the green arrow villain created by Kevin Smith. Also, in case you're curious, it's something that it's one of those words that is, it's like a sound. You know what I mean?